Hi, my name is Peter Jareb. I'm not an electrical engineer. I've got 24 years experience working for a couple different West Coast utilities. I've worked as a supervisor, as an electrical technician, and as an electrician. We're going to go over transformer vector groups, Y delta or delta Y transformers, and what happens if you apply backwards phase sequence to them. So instead of 1, 2, 3 or ABC, if you apply 1, 3, 2 or ACB phase sequence to them. So on the bench, we've got a Manta 5100, and that's going to be our voltage source. We've got a Megger PMM2 that we're going to use as a phase angle meter. We've got 3 single phase transformers, and what we're going to do with these 3 single phase transformers is we're going to connect them in a YD1 IEC, or like this. This is the transformer nameplate that we're going to emulate. So in this exercise, we're going to go ahead and walk through the connections, make sure that we connect these transformers like this nameplate. We're going to apply voltage to the high side winding. That is ABC phase sequence. We're going to observe the phase angle relationship between the secondary and the primary and confirm that it matches the nameplate in this. And then we're going to go ahead and switch things up, and we're going to swap the phase angles on our channel 2 and channel 3, or B and C, and we're going to apply ACB or 132 phase sequence to the same transformer. We're going to witness the phase angle displacement between the primary and the secondary with the phase angle meter, and what you will see is that if you apply a backwards phase sequence to a delta Y transformer, you also invert the relationship lead lag between the primary and the secondary. So if we apply backwards sequence, or 132 ACB to this, we're going to get, instead of it being a 30 degrees lag on the secondary, it'll be 30 degrees lead. So I'll leave it to that. We're going to get into the different parts of this video. Build this transformer on the workbench. And this is a YND1 transformer. So the high side, you can see these H's very well, is a Y. And the low side, these X's, are delta. And here's my H1 and here's my X1. And it's called a YND1. The 1 comes from the fact that the secondary is lagging the primary by 30 degrees. So if we were to draw a clock with 12 o'clock being here at my H1, my X1 would be at 1 o'clock, or 30 degrees lagging my H1. So that's what we're going to build. And here is the IEC kind of simplified drawing of a YD1. And what we're going to witness in this test is that as long as we apply, ABC or 1, 2, 3 phase sequence to this transformer, we're going to observe that the secondary lags the primary by 30 degrees. But what happens if we apply 1, 3, 2 phase sequence to this transformer? And what we're going to witness is that if we apply 1, 3, 2 phase sequence to this, now all of a sudden the secondary leads the primary by 30 degrees. So in this teeny tiny transparency right here, we have this exact same vector group printed out on a piece of transparency. So exactly the same. And you can see H1, H2, H3, X1, X2, X3. And with it being that if you had a little stick person right here and this was rotating counterclockwise, it is 1, 2, 3 phase sequence. So this is normal. This is ABC, or 1, 2, 3 phase sequence. This is the way the transformer nameplate is drawn. Now, if we were to actually apply 1, 3, 2 phase sequence to it, so it's very hard to see, but this is H1, H3, H2, X1, X3, X2. Now, my secondary is leading my primary by 30 degrees. We've now turned this, the YND 1 into a YND11 by applying backwards phase sequence to it. So why this is important is that if you had two transformers that were identical and they were wired up where one transformer saw ABC phase sequence and the other had ACB, and you tried to parallel the secondaries, there would be a 60-degree discrepancy between all three phases on the secondary, and that wouldn't work out so well. So we're going to go ahead and move into showing the setup. Okay, so the next step is I've got 3 single-phase transformers here. And the way I have them set up, I've got 160 turns on the primary and 80 turns on the secondary. So in the primary is the voltage source for the Manta. So I've got VA or V1 going to quote-unquote H1, V2 or VB going to H2, V3 or VC going to H3, and then I've got, you know, the HO kind of start up and returning back to the test set. So that matches this. And then on the secondary side, we're going to go ahead and call this X1, X2, and X3. And what we're going to do is make this up in a way that matches this so that we have a YD1. So I'm going to take and use my first jumper to connect
Misspoke.
Spot of 1. Well, this is the spot of 1 to the non-spot of 3. And you can see that I've got spot of 1 to the non-spot of 3. Now I'm going to take the spot of 2 right here and connect it to the non-spot of 1. And then finally, I'm going to take the spot of 3 and connect it to the non-spot of 2. Now, these other leads you see on here, this set and this set right here, are going to a Megger PMM2 phase angle meter that you're going to see in a second. So I'm going from 1 to 2 and 1 to 2. All right, to more setup. Let's take a second and go over the configuration of our voltage source. So we're using a Manta 5100. I'm going to be applying 20 volts phase to neutral, and we're going to be doing it with A, B, C phase sequence to begin. The phase angle convention on the test set and later, as you'll see on the phase angle meter, is 0 to 360 positive lag. It is this way because that is the preference of the utility that I currently work for. All right, demonstration time. Camera work's going to be a little shaky because I got to hold it. So Manta is on. We are A, B, C, or 1, 2, 3 phase sequence. We're going to come on over to the phase angle meter, and you saw that we had 20 volts phase to ground, and the phase angle meter is connected, 1 to 2 or A to B on the H side of the transformer, and 1 to 2 or A to B on the X side of the transformer. So on the H side, we're seeing approximately 20 volts times the square root of 3, which is what we expect, and on the X, we're seeing 10 volts-ish, which is what we expect. Phase angle, we should be expecting 30 degrees. It's a little bit off. I did this exact same exercise yesterday with a 6150, and it was spot on. So I'm suspecting that the Manta is not quite healthy. So Again, phase angle convention here. We're 0 to 360, positive lag. The red arrow is the high side. The yellow is the low side, so H and X. And that matches up with what we're seeing. The low side is lagging the high side by 30 degrees, which is what we are expecting here. So now, while we have you on camera, we're gonna go back over to the Manta. We're gonna shut her down. And then we're gonna go and we're gonna flop the phase sequence. Go ahead and turn it on. So now we are A, C, B, or 1, 3, 2 phase sequence. So let's go ahead and move back over. Nothing's changed as far as physical wiring. Again, our A to B phase to phase voltage is about 20 volts times the square root of 3. And on the X winding, it's about 10 volts. The phase angle is 30 degrees leading, as in the secondary is leading the primary by 30 degrees or lagging by 330 degrees. Again, approximate because of the test source. And here is our high side, and here is our low side, or X. So that's the demonstration. Summary. On a transformer, if you want to maintain the vector group that is shown on the nameplate, you need to apply a phase sequence of 1, 2, 3, or 2, 3, 1, or 3, 1, 2, which are all basically the same thing. If you were to apply a phase sequence of 1, 3, 2, it would mirror the vector group, and you would observe, instead of, in this case, the secondary lagging the primary, it would lead the primary. So this brings on another question. What do utilities do that have ACB phase sequence? The answer, at least in my observation, is that utilities that have ACB phase sequence always connect that relay's, or I should say, that utility's A phase to H1, that utility's C phase to H2, and that utility's B phase to H3, holding true the 1, 2, 3 phase sequence, and therefore keeping the vector group on the nameplate true.